In this video, we're going to continue our conversations about rational functions, and we'll just go and start and see what we can remember from our first conversation. So I think what might help is just to tell yourself that in most cases, rational functions are going to include some version of a vertical asymptote or two or three, and a horizontal asymptote of, there'll just be one of those. So that's a typical expectation. Probably there's some places where we're going to have some zeros. We'll probably have a y-intercept, right? So if you could just keep in mind that in general, we're going to have graphs that kind of do, some version of this, then just keep in mind those are the things we need to look for: horizontal and vertical asymptotes and zeros and intercepts. That's it. Or you can summarize it more to just talk about, just like polynomials, it has end behavior, it's got zeros, it's got intercepts. So, what are the intercepts? What are the end behaviors? What's the domain? All of those are very relevant questions. Okay. So this first one, someone has done the heavy lifting for us and factored it for us, which is great, except for the part where I want to know about the degrees of the numerator and the denominator. This is where this problem's a little bit annoying for us. That's okay. We can figure it out. So I'm just going to think about, f of x is approximately going to be what kind of a function. So on top, I've got an x times an x times an x. And so this is going to be an x cubed. The bottom is going to be an x and x and x, also an x cubed. Okay, so since the degrees are the same, now we need to know also the coefficients. So let's take another look. This is a 1x times a 1x times a 1x times a 5. So this is going to be a 5x cubed plus a bunch of other stuff I don't care that much about. And the denominator is going to be an x times a 2x times a 2. So that's going to be a 4x cubed plus a bunch of stuff I don't care about, which tells me my horizontal asymptote is going to be the ratio of the leading coefficients. So y equals 5/4, 1 1/4. Okay. The other thing that's a little bit more annoying in this format is the y-intercept. So the y-intercept is when x equals 0. And so I want to know what f of 0 is. So again, in this format, it's a little more annoying to find out. On top, if I plug in 0, I get -3, 0 times 1, so it's -3, times, plug in 0, -5. So -3 times -5 is +15 times a 5. And so that's going to be 15 times 5, which I think is 75. That's not my y-intercept. That's just the numerator. Plug in 0 on the bottom, and I get 4 times -7. So that's going to be what? -28. Plug in 0 in this term. Clicker's not working. And I get a positive now, 28 times 3 times 2. So this is going to be, I lost track, 28 times 3 times 2. So 6 times 28. So this is kind of a major pain in the butt, but still better than factoring. So 6 times 8 is 48. 6, 12, 34, 168. So this becomes 75 over 168. And that's going to be what? A number slightly smaller than a half, because 70 over 140 would be a half. So this is 70 over 160. So something smaller than a half, but still in the range of a half. Okay. Not sure how helpful that's going to be. Maybe we won't even need it. But usually that's pretty easy to find. Okay, so now let's get the main pieces that are left. And the main pieces that are left are going to be my zeros, and that's going to be only when the numerator is 0. So x equals 3, x equals -1, x equals 5. And my vertical asymptotes. That's going to be when the bottom equals 0. So that's going to be at 3/2, at 7, and -4. All right, let's see what we know. Okay, vertical asymptotes at 7. So I'm just going to jump way out here. X equals 7 at 1.5. And at -4. I have a horizontal asymptote at 1.25. So we're just going to estimate that right here. That's at y equals 5/4. Okay, zeros, +3. So that's going to be somewhere in here, also 5. So I've got a 0 at 3. I've got a 0 at 5. I'll label those in a minute. I also have a 0 at -1. Okay. I guess the last thing I have is this really weird y-intercept of around 1/2. So I know that that's going to be right in there. And I think I have enough. Ooh, almost. So this has broken up my graph into 4 distinct parts. 3 of the parts I know for sure. Absence of points over here on the far right side. I have no points. So the graph has to be up here because I did not cross the axis at all. Middle could be a couple of things. We'll come back to it. Or not middle, but that side. The only way I can cross to this point and hit my vertical asymptotes is if it's doing this. It's got to be either going up or down, but how can I be down, hit that point, but not have any zeros here, right? It's impossible. So the only option is this. I suppose there's a random chance it could bounce up off of that point, and we could certainly check for that. But if I'm really low on time, I'm feeling 99.9% confident in that answer. And then the far left side, I have no zeros. And again, the absence of points is data. So the only part I don't know about is this middle section. So I don't know if it's coming up and passing through and then coming back down, or if it's doing the opposite and coming down, passing through, and then coming back up. Shy of it doing a weird bounce on one of them, this is what the graph would have to be doing. Okay, so I'm going to do some quick investigation. I'm going to ask myself the question, what's going on as x gets close to 7 from the negative side, from the left? What's y doing? So I'm going to think about a number like 6.99999. And I'm going to go up and do some analysis on the factored version of this graph or this function. So 6.999 minus 3 is a positive number. Plus 1 is a positive number. 6 minus 5 is a positive number. On the bottom, 6.99 is about 12 minus 3. That's a positive number. 6.999, almost 7 minus 1 is almost 0, but it is technically negative. And 6 point blah, blah, blah is positive. So on the top, I've got positive. On the bottom, I've got negative. Positive divided by negative is negative. So I know that I'm going down to negative infinity. Therefore, I feel really confident in this answer right here. And if I want to really double check that there's nothing weird going on, I could just do the following. As x goes to 1.5, right? 1.5 or 3 halves from the right side. So I have to pick a number that's definitely between 1.5 and this 0. And this 0 is at what? At 3. So I could probably plug in 2, and that'll be good enough, right? They'll tell me. So what happens when I plug in 2? Let's redo our positive negatives. I plug in 2, and I get a negative. Plug in 2, I get a positive. I plug in 2, I get a negative. Negative, negative is positive on top. I plug in a 2, I get a positive. 2, I get a negative. 2, I get a positive. Positive, negative, positive is a negative on the bottom, and I'm going to negative infinity, which is what I assumed I was doing. And so that would be a close approximation of my graph. I really should label these points. I'm going to move on for the sake of time in this video. All right, part C. Let's look at the degrees. Ooh, I have a weird situation here. I have a degree on top that is bigger than the bottom. That means no horizontal asymptote. The other thing that's easy to figure out in this form before I factor would be the y-intercept. Does it have a y-intercept? Let's see. Let's plug in 0, and I get negative 16 over 2. So it looks like I have the point 0, negative 8. So the only thing left to figure out now is like a domain question. And before I do anything else, I'm going to factor this. So y equals, or attempt to factor it, I should say, x, 8, and 2. Make 16 negative 8 plus 2 over x plus 2. Now, this is an interesting problem because what we've just found out is that there is a common factor top and bottom, and I know that I can factor out and cancel any common factor. So what we have found is that this graph y equals that they've given us is exactly the same as y equals x minus 8. However, I have to be very careful. I still can't, even though plugging in negative 2 to this simplified problem here gives me an answer of negative 10, I'm still not allowed to use negative 2. And that's because the graph that was originally given to me is this one. And if I plug in negative 2 in the denominator of this one, I get undefined. So if I want to say that y is equal to this original graph, and I want to say y is equal to this, that's kind of a lie. But I can correct that lie by just saying, hey, if you want to graph y equals x squared minus 6x minus 16 divided by x plus 2, you know what you can do? You can just graph y equals x minus 8 instead, as long as you don't include the negative 2. If you exclude negative 2, so this is a little restriction on our variable. These graphs, if we put them on a calculator, they're going to be exactly the same, except on this one, I've got no issues at negative 2, but if I graph this one, I have an issue at negative 2. So I have to account for that issue, and I'll pull this all together in just a moment, because this is like my third video of the day, and I might not be doing as good a job as if it was my first video. All right, so what have I learned? No horizontal asymptote. There is no vertical asymptote. In fact, I am just going to graph the line y equals x minus 8. Notice it has a y-intercept of negative 8, just like this does. So I'm going to come down to negative 8, and I'm going to have a slope of 1. And so I have a graph that looks like this. This is the graph of y equals x minus 8. But I'm not supposed to be graphing y equals x minus 8. I'm supposed to be graphing this function, which is almost y equals x minus 8. The only difference is I'm not allowed to use negative 2. So I'm going to go to negative 2, which we can plug in and see that that would be the point negative 2, negative 10, right? If I did use it, I'd have the point negative 2, negative 10. We have to remove that point. So I come to that point and I actually just remove the graph here. I move and I take out, come on, computer, stay with me. Yeah, it's not behaving. Is this going to erase? So that's going to erase. Let's try this. There we go. So we have that line that we drew, but I have to remove the value here at negative 2, negative 10. So that's the location of the hole. So the graphs are the same, except for the fact I can't use negative 2. And that now this is the graph of y equals x minus 8, except x can't be negative 2, or it's the graph of y equals x squared minus 6x minus 16 over x plus 2. If you graph it on a calculator, the hole will not show up. But if you then tried to plug in that negative 2, it would give you an invalid answer because you'd be dividing by 2. Okay, let's see what happens on the next one. Example number 1, find all relevant information and then graph it. Label the information on your graph. Notice right off the bat, the degree on top is higher. So this is, again, a no horizontal asymptote. If I plug in 0 for x, I get 0 on top and negative 1 on the bottom. So that means my y-intercept kind of appears to be right now 0, 0. But before I really do anything else, I really should factor this. So I get x times x squared minus 1 over x squared minus 1, and x squared minus 1 cancels out. So this graph is really just the same as y equals x. Oh, except, you know what I can't do? If I had gone ahead and gone a little bit further, and maybe I'll go ahead and do that. Let me factor the top and bottom completely. The top is going to factor into x squared minus 1, which is x plus 1, x minus 1. And the bottom is going to factor into x plus 1, x minus 1. And so they're all going to cancel out. And I get y equals x. But you know what? X cannot equal negative 1. And it can't equal positive 1. Because if I plug those into the original, I get undefined. So what this tells me is I don't have to mess around with anything to graph this rational function. You know what I can do is I can just graph its lookalike, which is y equals x. Oh, you know what? But I'm not supposed to graph y equals x. I'm supposed to graph y equals x everywhere except for when x is negative 1. And when x is negative 1, y is negative 1. So I need to come here and leave out this point at negative 1, negative 1. And if x is positive 1, I get positive 1. So I need to leave out this point at 1, 1. So what I really have are two holes located at these 2 points. So I have holes at 1, 1 and negative 1, negative 1. And again, to find the y value that goes with the whole, I'm just evaluating at this newer, easier function. Because what I'm telling you is that this graph that they gave us and this graph that we simplified to are 99.999% the same. The only thing I have to do is modify this easier graph by removing the points I'm not allowed to use. I had graphed the point 1, 1 before, and I shouldn't have done that. So I'm going to, my eraser allows me to, and it does not appear that it's going to. There we go. Oh, I need to remove that point, and then I need to remove the point at -1, -1. And there's my graph. No vertical asymptote because once I simplified, I had no denominator to worry about. So I have, I'm just graphing y equals x. Okay, let's look at this one. Let's think about end behavior. And if you prefer it, you could rewrite this as -3x plus 1 over x. So my degrees are the same. So I have a horizontal asymptote this time at y equals -3 over 1. I have a y-intercept. When x equals 0, I cannot plug in 0. So I have no y-intercept. So now I think it's time to think about domain and zeros. Now, in this problem, x is not a factor. X cannot cancel out, so we don't have the same situation that we had above. We do not have a hole. What we have is a vertical asymptote because I cannot simplify this problem into something that doesn't have a vertical asymptote. It is what it is. So when is the bottom equal to 0? That'll be when our vertical asymptote is. And that's going to happen at x equals 0. And does it have, let's see, what else is left? The zeros of the function. The top is going to equal 0 at, looks like positive 1/3. Subtract 1, divide by 3. -3 is 1/3. So that means I have the point 1/3, 0 as an x-intercept. Let's put it on a graph. Horizontal asymptote at -3. Vertical asymptote at 0. Label. I have no y-intercept, which is obvious because I can't have 0 as an input. And what else did I find? I have a 0 at 1/3. Horizontal, y-intercept, vertical, zeros. Do I know enough to graph this? I would argue that I do. And I have a 0 here. And so that means I came down, approached my asymptote from above. Here I have no zeros, so the absence of zeros tells me my graph looks like this. All right, let's keep going. I've squeezed one in right here. I'm probably going to need some more room. Okay. I'm going to factor it probably to start, just to take a look because things look kind of interesting here. This becomes x plus 4, x minus 4. So nothing cancels out. So I have to graph this function. I have to analyze it as it is. And so now let's kind of back up a little bit. Let's look at the degrees. Degree on the bottom is bigger. So I have a horizontal asymptote. At bottom's bigger, so that's going to be y equals 0. I have vertical asymptotes. At the bottom being 0, so that's at -4 and +4. I have zeros of the function when the top equals 0, so that's at x equals 2. So that's the point 2, 0 as an x-intercept. Horizontal, vertical, the only thing I don't have is the y-intercept, which is probably the least important, but still helpful. 0 gets plugged in. I get -2. And I could probably just go back to the original on this. I get -2 over -16, which is 1/8. So I've got the point 0, 1/8. Let's see if this is enough information or if I need anything additional. Okay. Horizontal asymptote at 0. Vertical at 4. And -4. Horizontal verticals of a 0 at 2, 0. And a y-intercept of 1/8. So I've got 2, 0 and 0, 1/8. All right. I think the inside is very clear what happens because there's no way I can be going through this 0 at this intercept, without having any zeros over here. So I can't be going down, but I have a 0 there. So I have to be going down on that side. All right. Sometimes the absence of points is information itself, as it was in this previous question. The fact that I had no zeros here told me I had to be on the bottom of that asymptote. But that was because the asymptote itself wasn't at 0, right? So then that combined with the no zeros told me what it had to look like. I'm not so lucky here. The absence of zeros doesn't really tell me anything about whether it's above or below. So this one is going to require a little bit of quick analysis. And I can do this in my head, nice and simple. I'm going to plug in a number like infinity. I don't really care what's happening up close to the vertical asymptote so much as I care about, because whatever, if I get a positive, then I'm up here. If I get a negative, I'm down here. So it doesn't matter what I plug in. It just has to be bigger than 4. So I would suggest plugging in a billion, right? Something entirely huge. And usually I would do this by now looking at the factored part. But I think the answer is maybe just as obvious on the other, but let's do it on the factored part. I plug in a billion and I take away 2 and I get a positive number. Plug in a billion and I get a positive, a billion, I get a positive. I get positive over positive. My graph definitely looks like this. So now I'm just going to repeat the same thing. I need to pick, come on. I need to pick a value like -10 billion, see what happens. So I plug in -10 billion minus 2 is a negative. A negative minus 4, that's going to be a negative. Negative plus 4 is going to be negative. I have a negative divided by a positive, which is a negative. My graph has to be going down. And there you go. So just because you have to do a little bit more investigation is not necessarily a huge deal most of the time. All right. And I think as our last example, I look at this and automatically horizontal asymptote. 0. Y-intercept. Plug in 0, everything disappears. Oh, I don't have one. Because if I put 0 in the bottom, I get undefined, which then tells me, hey, maybe I need to think about the domain. So let's factor the top. 6 times 3 is 18, 6 minus 3. So looks like we've got a 6 and a 3. And positive 6 minus 3. On the bottom, I'm factoring out an x first. And I recognize that as a perfect square trinomial, but if you didn't, multiplies to be 16, adds to be 8, has to be 4 and 4. So f of x simplifies to be x plus 6, x minus 3, x times x plus 4 squared. I'm just going to write it out separately. All right. So this is all pretty simple. Most of this you could just do in your head. Just the writing it down kind of takes the extra second. So what do I know? I know my zeros are at negative 6, 0 and positive 3, 0. I know my vertical asymptotes are at x equals 0, x equals negative 4. So I think that's everything I know. So let's see what we've got. Okay, vertical at negative 4. Vertical at 0. Okay, did that. Horizontal at 0. And again, for what we talked about in the last problem, I don't really like it when my horizontal is 0 because often I don't have enough information just to figure it out. And zeros, negative 6. So that's out here. And negative 4. Nope, 3, excuse me. Okay, so this is interesting. I have very little information, and I have something that seems odd to me, but this will happen from time to time. So let's analyze the far right side of the graph. Once again, what is it that I can sort of come to the conclusion of? I know I either have to be going up or I have to be going down. I also know I have a 0 right there. So the only conclusion I can come to is that this graph will come down and pass through. But we know that eventually, as x goes to infinity, we get a number close to 0. So it would have to end up kind of coming back up and settling at 0. Putting together the understanding of what happens at asymptotes, and I have a 0, that's the only conclusion that I could make unless it's coming up from this asymptote, passes through this 0, but then eventually we know that it has to stabilize back close to 0. So eventually it's going to have to come down and do this. Those are the only real things I can think of that could happen. I suppose it's not out of the realm of possibility that it could come down and bounce off and then settle down. So maybe it comes down and then bounces here and then does this, or the opposite from the underneath side. I don't know is the whole point, and so I just need to do some investigation. So I'm going to erase all this stuff and see what we get. I really need to restart my computer. Okay, here we go. So I'm going to plug in a very, very, very large number for x, somewhere in the neighborhood of 1 billion, and I'm going to go to my factored and see what I get. A positive number plus 6, a positive number minus 3, a giant positive number is positive on both. And then, I should be analyzing it here. And then a positive, and this is squared, so that's always going to be positive. That's positive. So I know that I am eventually above my asymptote because I've got a tiny little number close to 0, but it's going to be a positive. Now, probably that means it's going down at 0. But let's just double check. Let's do an investigation of 0.00000001. I put that into my factored version here. Wish my clicker was working. 0.001 plus 6 is a positive number. Minus 3, that's a negative number. So this is actually negative on top. positive, positive, positive on bottom. A negative divided by positive is a negative. So this is doing what we had kind of discussed. It's coming up, and then it eventually is settling back down to look like this. So let's do the same analysis on the far side because it's got the same situation. So I'm going to plug in negative a billion and analyze the second line right here. Negative a billion plus 6, negative a billion minus 3. Those are both negative. A negative times a negative is a positive. So I have a positive on top. Negative a billion is a negative, and a negative. That's 3 negatives. That's a negative. So I have positive on top and negative on the bottom. I have to be going down. It has to be a negative. Excuse me. That's a lie. Not there. So I know I'm underneath the graph here because I got an answer that's negative. So I think what we have is the scenario that we're going to come down and we're going to cross back up. Let's find out. Let's plug in negative 4.00001 and see what happens. Okay, on top, I get a positive, I get a negative, I have negative on top. On the bottom, negative 0.40001 is a negative, times a negative, times a negative is a negative. Negative over negative is positive. That confirms I'm going up. Okay, now I've got the middle section. And the good news there is it either has to be going up on both ends or down on both ends because I never cross through the middle. And so I just need to do one quick test and it'll answer all of the questions. So I'm going to plug in negative, a very tiny little negative number, or you can just, pick any number you want between 0 and negative 4, like negative 1. And whatever I get, it'll tell us what the answer is. So let's just plug in negative 1, see what happens. Negative 1 plus 6 is a positive. Negative 1 minus 3 is a negative. A negative plus 4, and a negative plus 4 are two positives. And so I've got a positive, a negative, and a positive. That means I've got negative over negative, which is positive. So I know my graph looks something like this. I don't know how far down this goes. I don't care, but this would be my graph. All right, lots to analyze, but if you have good number sense, then it's all pretty straightforward. You'll notice I'm not talking about memorizing anything. I'm just thinking. So that brings us to what we've been talking about. And I think this covers everything except for one piece. So we talked about holes. Those are also called removable discontinuities. And the reason it's called a removable discontinuity, now it's a discontinuity because there's a break in the continuity of the graph, right? I'm graphing, I have to stop, I have to put a hole, and I have to keep going. So it's not continuous. But the reason it's called removable discontinuity is because I can remove the discontinuity. I can plug this thing up and make it continuous by sticking in, if I were to stick in 1 point, and I have removed the discontinuity. I'm not saying we're going to remove it. I'm just saying we could remove it by plugging that with with a single point. So that's called a removable discontinuity compared to a vertical asymptote, right? Where the graph might be going up and then might be doing this. I cannot plug this hole with a single point, right? Nothing plugs that hole. So that's just a discontinuity. They're both called discontinuities. The hole is just called a removable discontinuity. Doesn't really matter. It's a hole. So these two guys are talking about the same concept. What are the values of x that I can't use? End behavior is a discussion about asymptotes. What function does the graph mimic when the magnitude of x is very large? It's going to be some sort of line. So it's either going to be a horizontal asymptote when the degree is either, well, let's see, I've broken this down into two different ways here. A horizontal asymptote when the degree of q of x is greater than or equal to the degree of p of x. So that is if we're looking at a function where we have p over q, right? So p of x over q of x. So what am I saying here? If the degree of q of x, the bottom, is greater than or if it's equal to p of x. So that's what we've been talking about. If these are the same degrees or the bottom is bigger, then we'll have a horizontal asymptote. Tomorrow, we'll talk more about the slant asymptote, which is when the degree of the top is bigger. X-intercepts, that's when y is 0. In other words, when the top is 0. Y-intercepts, we let x equals 0. And then if you need any other information, then we have to just plug in our values. See, so memorizing it seems like a really big pain in the butt. I don't recommend it. I just recommend you think about what we've been talking about. Can't divide by 0. What happens when the function is 0? What makes the function 0? And thinking about number sense. Okay. I hope I'm not making this harder than it should be. I don't know how many of you are even watching these videos, but if you have any questions, please reach out and ask.